Hi everyone, and welcome to my latest video. It's been a while since I've uploaded anything, and I was thinking today that there are probably things about indexes on SQL Server that a lot of people, a lot of full stack developers particularly, don't understand, and I thought it would be a good opportunity to kind of do a beginner's guide on indexes and how they work. Now, just some kind of stuff to get you ready. I'm using this Wide World Importers database. It's a Microsoft test database. You can download it yourself, and everything that I'm doing today is based on this, and I haven't really changed it very much. So if you want to kind of follow along with what we're doing, download and install Wide World Importers, and this is just Management Studio. I think this is version 2019 SQL Server with a developer edition. So that's all there. And kind of really my motivation is I meet a lot of people. I am a development manager, and I interview a lot of people who call themselves full stack developers, and they have maybe 10, 15, 20 years experience, and you ask them what they know about databases or about SQL Server, and they kind of say something like, well, yeah, I can create tables and I've written views and stored procedures, as if that's kind of enough. And to me, these are all day one skills. Creating tables, writing views and stored procs is all very much kind of, beginner stuff. And I think if you're a full stack developer, it's essential that you understand what makes SQL queries slow and how to speed them up. And probably the main way that we do this is by using indexes. Now, this is going to be based on SQL Server, which, as you will probably know, is a very common database engine. It's what I use mostly, so I'm very familiar with it myself. But most of these principles apply to all other SQL engines. So your Oracles, your Postgres, and all the rest of it all have all support indexes, and they will all basically benefit from the same types of things. The only thing that might be slightly different is the syntax in some cases, but I think largely this should be good for all of these other engines as well. And we need to start by thinking for a second about how data is stored in a database. So if you create a table in SQL Server and you don't specify a primary key for it, then the table is stored in what we call a heap. And the heap is effectively a list, an unordered list of pages. And these pages, although they might look like a kind of a useful format, because there's no kind of ordering, then it's not optimal for any kind of query, because a query works quickly when the engine can work out where to go to find the data. And the way it does that is by ordering either the table or non-clustered indexes, which we'll look at later. So searching for anything in the table with no index always performs the worst kind of search, and that's called a table scan. Now, the table is a series of pages, but they don't necessarily live next to each other on disk. So we're not necessarily talking about one very large file where all of these pages are next to each other. If you know your computer science, this is more like a linked list of data pages. But as far as you're concerned, logically, these pages are in a certain order on disk, and that's kind of important. So let's have a little look here, example of creating a table without an index. And what I've actually done is just using this Wide World Importers database. I simply took the invoices table, which is created by the backup that you download, and I selected into invoices 2 all of the columns from invoices. So this has all of the rows that invoices has, but if you notice, if you know anything about SQL Server, there are no keys, there is no primary key, and so it hasn't copied any of that. The only thing it's copied are the column names and types and the data in them. So we're going to make a select call initially on invoices 2. Notice that these have a schema name, so you have to specify the schema name as well as the table name here. And one thing that's really important when you're doing any work around profiling and performance checking, you need to make sure that little button there, Control M, include actual execution plan, is enabled. and you can see one down the bottom at the minute. Don't worry about this one particularly, but this is the thing that's going to give us the information that we need to know. So this is what we call an well, it's not an unclustered index. It's nothing. It's no index at all. And if we run that, we get a result. So we're looking for a specific invoice number. We get a result with all the data, so it works. And when we look here at the actual execution plan, it tells us that this took place with a table scan, which is, yeah, like the worst of all worlds. Effectively, the engine has had to go through every single table in invoices 2 looking for something that has an invoice ID of 999. And you know, this is kind of the reason why we would never really create a table that has no index on it at all, because by doing that, there is no query here that can do anything other than a table scan, because there's no ordering at all to the table. So if we pop back then, and this is probably the biggest thing that you need to understand in terms of making sure that your queries are working efficiently, and that is the difference between seek and scan. So anytime a database query can use an index, it can very quickly compute where to look in the set of data to find what it's looking for, and we call that a seek. So that's good. If there is no index that is ordered by what we're looking for, so that if the ordering's not there, then the entire table or an entire index needs to be scanned in order to determine if the item exists or not. So that's called a scan, obviously. So hopefully you can appreciate that a scan is very significant and a seek can be very quick, going straight to something, even if you're going to say maybe a set of things, but that set is much smaller than the entire table, then that's going to be much quicker than going through the whole thing. In large tables, you mustn't underestimate the difference here. If you did a table scan on a table that has, you know, several billion rows in it, which isn't uncommon, then that could literally take you minutes, especially if something else is running at the same time and the query's waiting for a lock to be available or to be released or whatever. Literally the difference between these two can be minutes. A seek might take milliseconds, and the scan might take, like I say, a long time. So this is very, very significant difference. In terms of an analogy or a metaphor, if you like, for this, imagine if you're given a phone book and you need to look up the phone number for John Smith. Now this is really quick because the phone book is ordered by people's name. So I look up S for Smith, I find John Smith, assuming that there's only one in there, which is probably a bad example. I can find the page very quickly, and then once I've got the page, I can find John Smith very quickly. So that's like a seek. That's good, it's quick, it's easy. But what about if we were doing something slightly different? What if I said, find the name of the person who has this phone number? Now the phone book is not ordered by phone number. So I don't know whether that phone number is on the first page, the last page, or any page in the middle. And if I know there's only one of them in the whole phone book, then my average time to find it is I'm gonna need to scan through half the pages in the phone book on average. But sometimes I'll find it quicker, sometimes I'll find it slower. You can imagine that would take a very, very long time compared to looking up a number by a name. And remember, unless we use top in our query, then the query will always return all matching rows. So we've got to remember that if we know we're only going to get one item back, then we should be passing a query with top 1 in it, so that as soon as the database engine finds that row, it can stop looking. If you don't do top 1, it might then scan the whole thing, might find one, might find more, and then your code will then have to take the first one of those anyway. So that's something to watch out for. So this kind of brings us to the point of indexes, and an index is what it sounds like. It's an ordered lookup containing one or more columns from the underlying table. So just like any other index, because it's in order, that's what makes it easy to use, as long as your query is using columns from the index in its search terms. So if I have something ordered by person's name and I'm looking for somebody with a certain name, then because of the ordering, the system can very quickly find out exactly where that would be in the list, if it is there or not, and then we'll be able to either find it or return back 0 rows. The aim of indexes is to try and get everything where it's possible to use seek instead of scan. And like I say, the speed up is astronomical. The difference is like night and day. It's so important that we know how to do these. Ooh. So the first one we're going to look at is the clustered index. Now the clustered index is the main index of a table. And because of the way a clustered index works, it defines the ordering of the data in the table. And the ordering is defined by the columns that you choose for your primary key. So you need to realize that people will often use primary key and clustered index interchangeably. They're not exactly the same thing. The clustered index is based on the ordering of the primary key. And the reason that might be significant is if your primary key is something that you specify, let's say for example you use email address as a primary key, then if you insert a new user with an email address that exists, let's say halfway up the clustered index, then effectively the system might have to split those pages in half to give it some space to put your new item in. And that can be quite kind of costly and significant, which is why very often we will use an automatic an auto increment number and in that first column in that primary key, so the inserts will always go at the end, because whatever the data is, the number is always higher than the number that's already in there. So because it relates to ordering, there can only be one clustered index. You can't order the data by two different things. The data on disk, it can only be ordered in one way. And because of it being a clustered index, it always contains all the columns. And that's because, unlike a non-clustered index, which we'll look at later, when you get down to the bottom level, let's say in this little silly diagram here, if C, E and H were like the data pages, in a non-clustered index they would just be pointers to where the information is. But in a clustered index, these pages here are the actual data. So by definition, all columns are always available in the clustered index. Now, a primary key must be unique. In order to do that ordering, what you don't want in a database system is something that says, well, there are 2 rows and there's nothing unique about them and they could be in either order. That's generally not considered a good thing in data management. We want things to be uniquely identifiable. And if you do have a system where you have multiple rows that have the same data, you kind of have 2 choices. You can not bother with the primary key, not bother with the clustered index, but like I say, in general, that's to be avoided because it makes all of your queries of that table inefficient. And the other option is you add an artificial unique key. Like I say, it's very common if you've used databases, which most of you probably have. There's a row ID type columns, usually the first column. It's an auto increment number. So like I say, inserts always go on the end because the number always goes up. And if you have 2 rows that have otherwise the same columns, they will still have a different row ID. So this is kind of the clustered index. Like I say, primary key clustered index, sometimes used interchangeably. But we're going to look now, we're not actually going to create the table because it's already created. But if we look back here, so we looked at invoices 2, which was the table that I created with no indexes or anything on it. But the table that comes in the backup that you download already has a primary key, invoice ID. Therefore, by definition, it will also have a clustered index. And if I right click that, I don't think actually, if I script it, you can see what it looks like. You can't generally change the primary key because then you'd have to reorder the entire table. So these things are, once they're set, they're kind of set. But if you see here, it's a primary key, it's a clustered index, and it uses invoice ID ascending. So that's all the primary key is. But what I want to show you now is, first of all, if we run the same query against the table that's basically identical, except it has a primary key, and we look at our execution plan for this, we immediately see that we've got a clustered index seek. So we've hit the index, obviously. Once we create a clustered index, everything hits that clustered index if it doesn't hit one of the other ones. There's no table scans anymore. But notice we're getting a seek, and a seek is good, a seek is fast. And the reason we're getting a seek is quite simply because, by definition, the clustered index is ordered by the primary key. The primary key is invoice ID, you can see by that little black icon, and I'm looking for an invoice ID. So effectively that index is a list of these IDs ordered from whatever the 1 to a million or whatever they are, and so the engine can work out very easily where to go to find this. And because I'm selecting all of the columns, but because this is the clustered index, it already has all of the columns in it. We already said that, so it can hit that, it can do a seek, so that's pretty decent. It's not the best we can do, but what I want to now do is I want to compare the table that doesn't have an index with the one that has just a clustered index. It does actually have a couple of others, but we'll see that they're not being used yet. And the thing that I want you to notice here, and this is a really useful tool when you're comparing two different queries, notice here this line, query cost relative to the batch, query cost relative to the batch. What we're saying here is that the first one on the table that doesn't have the index was at least 100 times slower than the one that does have an index. So it's the same query, but just by adding a clustered index, it says here, I mean the numbers here are obviously quite small, so it's hard to know, but if you look here, it says the CPU cost is 0.00015. If you look at the CPU cost here, it's 0.0388, so that's significantly slower because it has to scan the entire table and to find invoice ID 99. It doesn't know without an index that that's even unique, so as far as it's concerned there might be loads of those, so it has to go through the whole table. With this, we'll see later how it works. It can use the clustered index simply to say, you know, is there anything in there of 999, and it's going to say yeah, there's only one in there, and it's here, and it will return it. So we can see here already, doing very little, that there's a significant difference. You do sometimes get these hints in Management Studio which will say, well, I've noticed you haven't got an index, here's a suggested one that you could add. Now, there's not a lot of wisdom in these. It might be helpful, but really you should be able to read these diagrams to work out when you have a problem. Seeing table scan is a problem. Seeing an index seek is good, but usually a non-clustered index seek is better, and that's really to do with locking, something we'll look at later. So, scroll down a little bit. When we query without the primary key, we saw a query with the primary key, and it was really fast, right? Because the clustered index is ordered by the primary key. So we use that index directly, we find, a bit like our phone book, look for it in the right order, find the right one, get it back. But if we query any other column, we won't be able to use the clustered index to seek, and we will get a clustered index scan instead. So let's show you what that looks like. So if we use, let's say, this one here. So we're coming from the same table, but this time our where clause contains a column that isn't in the index. The index only covers the invoice ID. So if I run this, we have the same problem we had with the non-indexed table, is it doesn't actually know how many of these there are. It can't work it out without going through the entire table. And as you can see here, we get a clustered index scan. It's got to scan the whole table. So again, that's really slow. If we compare that to an index seek, so these are both the same table now, but we can still see that the one that does the scan is over 100 times slower than the one that does the seek. So we need to be trying to do that. And why is this? Well, let's actually look at what happens. I don't want to go into too much detail here because it's probably going to be more confusing than helpful. But the data in SQL Server is stored in a binary tree, but it's a little bit misleading because a binary tree has a node which has 2 children. Each of those children has 2 children, and you keep on going until you get to the data that you're looking for. In SQL Server, that would make for quite a deep tree. So they tend to have, I don't know how many rows, but I think it's something like, it's either 20 or 50, I think, 20 children to each node. And each of those nodes can then have 20 children. So you can reach your data with a much shallower data structure. But what happens here, if let's say we're doing select star from user where user ID equals 51. So let's imagine user ID is the primary key. So because it's the primary key, these IDs in our pages, in our index pages, so this is the clustered index, are basically IDs for user ID. So if I want 51, I start in the root node, and this has ranges and says, well, anything between 51 and 100, you need to go to page 87. So then I go to page 87, and that further splits them down and says, well, actually, 51 to 61 is in page 453. The numbers are kind of a bit made up. They're probably completely wrong, but it kind of gives you the idea. And eventually you'll get to a page where you get an individual ID. So now you know that this is what we might call a leaf node. We're at the end of our journey. And on the clustered index, this is literally going to point us to the page that has all of our data on it. And it's going to say, you need to look in data page 8765. And lo and behold, we find ID 51, all of the columns that we need. So the nice thing here is rather than scanning down all of these pages looking for what we want, we can use a more binary approach where, 1 check, 2 checks, 3 checks, and we're there. So you can see why that would be much faster than going, are you the right row? No. Are you the right row? No. Are you the right row? Etc, etc. So why doesn't it work without the primary key? Well, if we only have a clustered index, so if we're only covering the primary key user ID, so this is the same set of pages. Now imagine I'm doing select star from user where email equals luke@example.com. Well, the information I'm looking for is not in the index. luke.example.com, I can't tell which of these IDs belongs to that email address. So what do I have to do? I have to scan down all of the pages and look for that email address. And again, if I don't put top 1 in there, it's going to read through the entire database, the entire table, because there might be more than one result, and it doesn't know without you telling it whether to stop when it finds the first one or whether to carry on. So how do we fix that? We fix this with a non-clustered index, and you can create 0 or more clustered indexes. You can only have 1 clustered index, but you can create multiple non-clustered indexes, and each of them can contain 1 or more columns in the actual index itself, so in the ordering part of the index. But the nice thing is they can also include additional columns. So if you're selecting columns but you're not using them in the where clause, you can include them in the index. We'll look at what that looks like in a minute. And to hit the indexes then, the query must only use columns in the where clause that are covered by the index. But the query can return additional columns like I just mentioned. If you want any other columns, so if you selected something that was neither in the index or in the included columns, the query will still work, but either your index will be completely missed out, and we'll look at that in a second, or the system will perform a key lookup, which means I've got some of the information from the index, but now I need to go and get the rest of it from the clustered index. And that key lookup is relatively expensive, so it doesn't always things don't always work as you kind of expect. So let's look here at some of the non-clustered indexes that we have in our database. So if we look here at these, the naming's a bit unfortunate. These are the names. Sorry, that's keys, indexes. These names with FK kind of relate to foreign keys, so they're misnamed. But don't worry, they're still indexes. And you can see here that almost all of these are individual indexes that have been created against one column. So if I look at properties here, you'll see that the column that's actually indexed, the one I can use in my where clause, is accounts person ID, and there are no additional included columns. So for whatever reason, that's how they've been designed. This is one that I've created, and that's just to demonstrate something a bit later. But let's have a look at this then. So we had a look at using start from sales invoices where invoice date equals blah. So we have two problems here. The first problem is that this column is not in any of the indexes, so it's not going to hit an index anyway, so we're kind of screwed before we've even started. But the other problem, let's run this one. So this one does have an index, so accounts person ID is covered by that top index, so this is a non-clustered one. But if we look at the execution plan, we'll see that it hasn't hit that non-clustered index. It's actually gone to the clustered index and it's done a scan. Now, why has it done that? Well, one of the main reasons is I'm selecting star. So I'm selecting all of the columns, and that index doesn't include any columns. So the engine's kind of said there's not really any point in me using the index. There are too many rows involved and you want too many other columns. If I'm going to go to the clustered index anyway, there's no top one, so I'm going to need to scan the whole thing. Might as well just scan the whole thing. So that's actually missed the index. So what happens then if we don't want all of the columns? What happens if we only want accounts person ID, where accounts person ID is 2001? So remember, accounts person ID is covered by the index. So if I run that, then hopefully, as expected, not only has it hit the non-clustered index, but it's also done a seek. And that's been super fast because everything in the where clause and everything that's been selected is already covered by the index. So that's brilliant. So the next question is, what happens here on the next line, or what would you expect to happen if we select accounts person ID, which we just did successfully, but we've now added invoice ID. Now invoice ID is the primary key, but it's not covered on this index. So I guess what we might expect to happen is that it will maybe find the people in the index and then do a key lookup to find the invoice ID from the clustered index. But what actually happens here, and this is something quite important, is that the index, although it doesn't explicitly contain the invoice ID, it does actually contain it as the link between the non-clustered index and the clustered index. So it's already in there, you just can't see it except when you run your query and kind of see how it works. So what happens here is, let's say we're using something that's covered by an index. So let's say now these numbers relate to badge number. They're nothing to do with user ID. Well, it works pretty much in the same way as the clustered index. It starts at the top and it keeps narrowing down the page until it finds the leaf node. Now the only difference here is a non-clustered index doesn't point directly to the table like a clustered index does. Instead, it contains the primary key, and it will be the primary key that allows the query analyzer to then do a key lookup into the clustered index to return any additional columns that we need, which is cool. Now you can see here, therefore, so these three boxes here are the non-clustered index. You can see if I want to select the column and the primary key, I don't actually need to go here. I already have the primary key, and that's why we always get that back for free, if you like. So we never need to include that. Now the other thing that's important here is that there are key lookups, but they don't always happen as expected, and I think I've got hopefully some examples here. So let's look at this one. It's kind of similar to one we've already looked at. We have that column and that column are both covered by the index, and I only want one more column, which will come from the clustered index. So I would hope it would use my index with a seek and then use a key lookup to get the credit note. But if you look, what's happened is what we've already discussed, is the engine's gone, nah, too many key lookups. Key lookups are slow. There's too much going backwards and forwards. If I'm going to do that, I might as well go through the whole table and scan it, because I'm going to have to go through it anyway. So we've actually ended up missing the key lookup. We don't get any benefit from our non-clustered index in this example. But what about this one? So I've done kind of the same thing, but I've changed it slightly. So the problem with accounts person ID in this example is there are lots of rows that have that accounts person ID, a couple of thousand of them. I'm not sure how many in total. Well, actually I am, because it will be there. 22,000 rows. So I've crafted a slightly different query. It sort of looks the same, but the customer purchase order is unique per invoice. So that means I'm not going to get thousands of rows. I'm only going to get hopefully one. I might get 0, but I'm only going to get one. And I've included this index here. So this index covers customer purchase order number, which wasn't indexed before. So that's why I've added this. And I've included accounts person ID. And the reason is that's in my where clause and that is in my select. So the right way to do it is create the index based on that and ordered by that, but also include that column so I don't need to do any additional lookup. And if I do this, you'll see here that it again doesn't need to do the key lookup because I've covered both of them. So let's revert this back and say, well, what happens if that column there isn't included? So let's say it will rebuild it, which is fine. Let's say I run that again. So this time I'm only covering this. So it's kind of the same as this query, only covering this column. The only difference being there are less rows. And the engine can work that out. And if you look, let's compare these two. If you look here, the top one, so they're basically the same shape. They're basically doing the same thing. The only difference is in number of rows. And the query analyzer is clever enough to say that top one is returning too many rows, so there's no point doing 22,000 key lookups. It'll just be really slow. So it just does a clustered index scan. However, for the bottom one, it kind of goes, oh, there's only one row of that. And because there's only one row, I can do the index seek and then just do whatever, a single key lookup, return one row, and and get a different execution plan. And again, something to note here is the difference in cost. So just by a subtle little difference there, that's again 100 times slower than this one. And if we then if we add in the additional column here and it doesn't need to do the key lookup, it's going to be even faster. The problem with that is trying to compare them, because if I take out that column or put it back in, then I can't compare these side by side, but that would be a significant boost as well. So like I said earlier, if we then include the column, I did this the wrong way around. If I include that as well, then I get a pure index seek, and that's like nice and super fast. So let's just go over these quickly again, just to do the reminder. The clustered index, there's only one of them. Might as well write that. Only one of them. Can have many of them. That's planning for you. So the clustered index is ordered by the primary key, and you can't change that later. Once the data's ordered, it's ordered. If you wanted to change it, you'd have to recreate the table, so that's destructive. It defines the table ordering and includes all columns. You don't get to choose that because it sort of is the data. And then a non-clustered index, they're ordered by the columns that you choose. So you design them to make your queries work. It does not affect table ordering because that's purely defined by the clustered index. And it includes only the columns you include rather than all of them. We noticed already it implicitly includes the primary key, which is very helpful, but only when selecting, not when doing your where. If you have the primary key in the where clause, then either use the clustered index like normal, or add it to the actual index itself. And you can have as many of them, or you don't have to have any of them. You have as many as you like. So let's look a bit at extending non-clustered indexes. So we kind of already looked at this a bit, but let's look here. What have we got here? We already kind of looked at this sort of idea about saying, well, I've kind of got this, it's doing a key lookup. And of course, we very quickly get into the territory that says, well, what happens if I just modify this? And what happens if I just chuck accounts person ID in there? Well, we need to realize that obviously there's going to be a cost to everything that we do on these tables. So now if I do that, the same query, I just get an index seek. So that's great, but there is a cost to that. There's a size involved, and there's the time it takes to actually modify data if you have too many indexes. But in many cases, if you have a table that's read much more often than it is updated or deleted from, then indexes are going to give you a massive win. And even if you do change the table quite a lot, if you're careful with your index design, you can almost always get a massive benefit by doing this job properly. So I wanted to just kind of show you a couple of things. There are these sorts of queries that you can find just by Googling them online, but this one's kind of interesting. It's the size of the indexes in the system. Now I'm just going to change the order by, because I want to look specifically for the one that I'm looking for. So let's order it by name. So in this query, if we look up non-clustered index 2020 blah blah blah, there we'll see that my index, which remember only includes 2 columns, but it's already 2 megabytes in size. And that doesn't sound like a lot, but actually let me select, try and select count start from invoices, because I'm not sure how many rows. Oops, sales stop. So that has 70,000 rows. So that's not actually a massive data. That's not a massive table. 70,000 is quite a lot, but we work with databases at work that have, you know, hundreds of millions of rows. So you think if this index is already 2 meg and it's just covering 2 columns, if we then start looking at, if we actually order it by, say, table name, let's go. Ooh. Let's look for our invoices table. So we can look here that the primary key is, which is basically the data, is 90 meg, so that's not too bad. We can see here that the foreign key sales invoices one, the top, is that the top one? Yeah, the top one we've already used, is nearly 1 meg, and the other one, like I say, is 2 meg. Now all of these other ones at the minute are disabled. I disabled them just so they didn't interfere with this tutorial. But you can imagine that, you know, not only can you get big indexes, sometimes the non-clustered indexes end up larger than the primary key, which sounds a bit nuts, but that's kind of how it works. So you can imagine if you've got 10 indexes and some of them are pushing on for the size of the table, then all of a sudden you're taking up 10 times as much space as it would if you had no indexes at all. So you do need to kind of balance that. So really the costs can be broken down into the additional data size, which on large databases can be significant. And if you think of tables that might be hitting hundreds of gig in size, then you start getting problems with individual hard disks and spanning across volumes and all sorts of stuff. So it's not to be sniffed at. And then the other one is there is an additional time. If you insert data in a normal clustered index that has a row ID, it will always go at the end, and that's great. No page splitting, no nastiness. If, however, you have an index that is ordered by something different, then there's a good chance that when you do an insert, it inserts at the end of the clustered index, but somewhere in the middle of a non-clustered index. And when that happens, just like it does with the clustered index, a page might have to be split to make space for this new piece of data. And if that page splitting occurs, the page gets locked, new pages get created, half of the data gets copied into each of these new ones, the two get linked up, and then the original page is unlocked again. So although that obviously happens in a very short period of time, you can imagine if that's happening hundreds or thousands of times a second because of the people using the system, then that could become a problem. And if you've got 10 or 15 indexes, the more of those that get split each time something changes, the worse it's going to be. On the other hand, if you've got data that doesn't change very much, then that's ideal for indexes. The additional locking, if you don't have enough indexes, is also what we're saying here is if you have a clustered index and no other indexes, yeah, they can all use that. They can always all hit the clustered index, but every time somebody locks a page, locks a row, all of those locks have the potential to block somebody else out. And of course, that problem gets exponentially worse as you increase the number of people using the system, especially if you've got something like an invoices table where probably everybody's always accessing the last 100 invoices rather than the previous 50,000. So there is a potential locking issue if you don't have enough indexes. So this question is often asked, how do I decide, do I want one index that covers, let's say, 8 columns, or do I want 8 indexes that cover 1 column? Well, there's kind of pros and cons of both. If you have a single large index, obviously you're using the least amount of additional storage because you're not duplicating data potentially across several indexes if you've got the same column in more than one. But also the highest chance of page splitting. If you're covering more columns, there's a good chance that any of those columns gets updated, then your index might have to reorder itself to say, well, this email address has changed, so now I'm not near the top, I'm now near the bottom. Again, I might need to page split, etc., etc. So all of that has got to happen synchronously before that data is allowed to be committed. So there can be an issue here. And obviously less indexes means higher risk of locking. If there's only one index, especially if people are often accessing the same data as each other, then you can have a problem. So then compared to multiple smaller indexes, so if we looked at this table, we saw it had like kind of 10 individual little indexes. Obviously that takes the most data storage, but only if you're duplicating stuff. All of those indexes will take up some space, but it's when you start adding columns that they're going to get bigger and bigger. So if you've got the same column in 3 or 4 of those, especially if it's like a varchar column, then you might be using a lot of data. But then you got a lower chance of page splitting, and that's because a page is only going to need to split if a change that you've made affects that specific index. So it's possible that a change affects one index and not another one. So by having smaller ones, you reduce the problem. But of course, one of them still might need splitting, but that's a smaller operation, is not going to lock out as many people as if you just had one big index. And then again, similar, lower risk of locking issues. So when you decide between them, you've kind of got to look at these things. Obviously, you only want indexes that are useful. So if you've got an index that you don't have enough columns in and it never gets hit, then there's no point having that index at all. So you probably need to at least look at your commonly used queries, and there are loads of different tools that can help you do that and to measure what the slow parts of your system are and those sorts of things. But really look at those and look at how you optimize those to work really well. One example was I worked on a system once where the address lookup procedure, it was from an accounting package, took like 30 seconds, which seemed kind of crazy to me, because looking up something by a piece of known data surely should be really, really fast. And it was just because of the way the person had written the stored procedure. So I kind of, knocked it around a bit and modified an index slightly. And then that thing that took 30 seconds now took less than a second. It kind of happened straight away. So, the gains can be good, but you do need to sometimes play around with them. And you might find an index that works well now, doesn't work well in 6 months, and needs deleting or augmenting or, removing or whatever. So, there's things to look at there. And so the last thing I want to look at, just to mention, is about fragmentation. So if we pop back to kind of this idea that we've got a load of pages, and in terms of the structure, although that's probably not a great diagram, this kind of thing that you have a root that has a number of children, each of those has a number of children, you've always got the danger of fragmentation. So what happens is, let's imagine that you've got something in one of these pages. Let's go back to here. let's imagine that all of a sudden you've deleted entry 52. So let's put the strike through there, however we do that. No, maybe we can't. Oh, that's rubbish. So let's imagine we've deleted that now. Now, if we delete that, the engine isn't going to go through and say, oh, I can shuffle that one up and then shuffle the next one up and then shuffle one from the next page up. It's just not going to do that because it would be incredibly inefficient. Instead, it does this. It just leaves a gap. It marks the row as available, as blank, but it doesn't do anything with it. Now, if that entire page gets wiped, well, that's not a problem because it's very quick to link the previous and the next page together. And to do stuff with that. But in general, what happens in most cases, you're going to get lots of little gaps like this all over the place. And we call that fragmentation. And you can see it in SQL Server. There's another query you can run. And just to kind of give you some idea. Now, remember that these tables were restored from a backup. So some of this fragmentation is really quite high. So 99% fragmentation on that table. And that's just because the people obviously who were using this at Microsoft when they were developing it were obviously just doing things, deleting stuff, adding stuff, not really bothering about the fragmentation. And then all of these fragmented indexes all got backed up. But let's just look at one of them, for example. Let's pick this one, foreign key application, city, state, province, ID. And let's look at how much space it takes up. Foreign key application cities. Let's go back to index name. Yeah, and again, it shouldn't be called FK. But anyway, FK. Oh, I keep forgetting. Application city, state, province, ID. Right. So at the minute, that's 880k. Now, that's obviously not massive. But let's see what happens if we defragment it. So that's 99% fragmentation, so that's pretty poor. So that is application, oh, moves up there, application cities. We find that index, it's that one there, non-clustered, state, province. So I hit that and I rebuild the index, click OK. Now obviously it's a relatively small table, and that is definitely the right table, yeah. And you can see that happened very quickly. But again, the engine is not going to assume that that's okay for it to do whenever it feels like it. It leaves it for you to do. So if we now go back and we find that one again, so just by getting rid of dead space, we've managed to cut, what, about a third of the size of that index. So the fragmentation is significant. If I go back to here and I run this again, you can see that that's now gone down to 0.2%. So whatever it's done, it hasn't gone down to 0 for some reason. I think it probably tries to do it quicker rather than perfectly. But you can see that's gone down massively, and the number of pages has also gone down. So that's another thing that we can look at. If we find one here that's very fragmented and has a lot of pages, like say that one, sales invoice line stock item ID, 99%, 616 pages. Let's see what happens to that when we defragment it. Sales invoice lines, indexes, F key sales invoice line stock item ID. So let's rebuild that. Okay, so we had 616 pages, sales invoice lines, and what's that? That's that one, isn't it? That's the one we did, stock item ID. So again, we've reduced the number of pages by nearly half. So, there's a significant gain to be got, and really you have a number of options with fragmentation. You either rebuild indexes manually, like I was just doing. So, of course, you can do that out of hours when you know the system's not busy or whatever. Or the other thing that's much more common is you run a job to do it. And if you do it more frequently, then there's less work for it to do, and the things are going to run quicker. So there are certain jobs that you can download off the internet that will say only defragment stuff that's more than whatever 50% fragmented or something, and you will help save on disk space. One of the things that's very strange about SQL Server is the way it uses disk space. It kind of allocates it and it doesn't really ever reuse the free space. So the danger is if you let something grow to 600 gig and then you kind of try and shrink it, it won't actually shrink. It will just create loads more available disk for it to try and reuse. But obviously the file itself gets fragmented as well. So if you don't want to end up needing massive disks just because your database used to be really big, then you need to try and rebuild these indexes kind of manually. And then just a quick thing really on joining tables. So we've seen stuff so far that's been pretty straightforward. It's kind of just one query, little bit of this or the other. But what happens if we run, say, a join? So we've got here the invoices, the table we've been using, and then we've joined people. And if you look here, we have a clustered index seek and an index seek. But you notice here we've got two individual selects, if you like, which is you'd expect for a join. And you notice here that because it hits both indexes, that's great. That's kind of what we want. If one of those was a scan, then we work on them individually. It means that, you know, we need to introduce an index in somewhere or other, or consider introducing one. But look what happens if we change it slightly. So this time, rather than using accounts person ID, which is covered by one of these, I think, which is covered by the one on invoices, what happens if we look for, say, employee equals 1? And what's interesting, again, we're looking at basically the same kind of query, but yet the execution plan's quite different. And again, the engine's quite clever, but we need to understand what it's doing so we can try and work out whether we need to fix this or not. So we've only run one query, so the whole lot's 100%. But what's interesting here is you can see the relative costs of each individual part. So 52%, so half of it was just doing an index seek. Now, if half of it is an index seek and an index seek is really quick, then possibly the fact it's doing a tiny bit of work on an index scan is not really a big deal, probably not worth fixing, because even if you got rid of that whole index scan, you're only going to save 8% of your whole thing, or maybe if you remove that, you'll save a bit more. So you kind of have to take a bit of value. But what's happened here is it's kind of managed to use two separate indexes. So rather than going to the clustered index and saying, I can't find anything on the first index, I better go clustered, it's saying, oh, if I get these two non-clustered indexes and use both of them, then I get to find the one that has the person ID in it, and I get to find the one that has the full name in it, and I can join both of those together and then use that as my data to join with the index from invoices. So this isn't really any different than anything else. This is a very simple example. I didn't spend any time building a complicated one, but you've got all kinds of weird things. You can have the key lookups, you can have sorting, ordering. I mean, sorting can be a really expensive operation. So often, if you can remove sorting from the query, then that's good, especially if you can do it on your web application more easily. Then you can cut, half the time off of your query. But all of these things, like everything, it might look complicated, but at the end of the day, it's all just loads of small things joined together. And if you hover over these, you can always see which object is it. So that is the people object, and it's using the index application people full name. And the two columns it's getting from that are person ID and full name. So the information is all in here to work out which parts of your query they are. And then with a bit of time, bit of effort, and a bit of experience, you can start working out how to deal with your more troublesome things. So that's it all really from me. In summary, seek and scan. We want seek. Seek means I've got something that's listed in order of what I'm looking for, so I can quickly find it. Sometimes if I can't fully seek, it will then additionally do a clustered index seek or scan. But again, the more we can use the seek, the better, the faster. And get used to using these tools. The execution plan is really helpful to work out what's going on. And like I say, in some cases where this is possible by copying things and that sort of stuff, then you can literally compare them next to each other and go, wow, those two things look quite similar in terms of the number of items, but that one's 100 times slower. So that's a clue to say, is this worth doing? And also, if you make an improvement, you run it again and see if it's made any difference. And if it hasn't, maybe you haven't quite understood what it's doing, or maybe you need to do a bit more. So anyway, hopefully you enjoyed that beginner's guide to indexes. I'm not a DBA, but if you have any questions about this tutorial, then please chuck them on the comments below. And otherwise, I shall see you again